Hey, hello, and thank you so much for watching this 12th chapter of the AI Red Team Academy. And today we are going to talk about embeddings and about vectors. And we are going to talk about how we make modern AI scalable and how we make raw data searchable. And that's exactly what we're going to do. We're going to take a look at different vector databases. We're going to see their importance while we run them in different scripts, and you will learn exactly what is happening in the background. So this lays another part of the foundation of artificial intelligence, and again, something you can use later on. So this is a pretty interesting chapter if you ask me. It is not that long, but it's not short as well. So there are still quite a few slides, but it is what it is. Like this video, please, because, well, this is a YouTube video and liking helps the video. Another thing that helps is subscribing to my channel. This will help me a lot. This will help my channel progress. This will help the course progress. And simply said, you will help my work a lot. So thank you so much for subscribing. And another thing that helps me a lot is by becoming a patron. And I know this is a paid option, and I know I'll ask this every video, but you will help me a lot because, as you can imagine, these videos simply take up a lot of time. And, well, a little bit of compensation is always nice. So when you become a patron, you will not only help my work, but you will get a lot of goodies yourself. You will get some extra lessons, you will get some extra videos, you can participate in workshops, you will also get the scripts that we use, maybe some extra scripts as well in the future, and you will get the slides, etc. You will get all of it if you become a patron. So please consider becoming one. Thank you so much for doing that. And by now, I think we are ready to start this 12th chapter. Let's take a look at embeddings and at vector databases. AI Red Team Academy, Chapter 12, Vector Indexing, where we will discuss 3 different vector databases, the FAISS, Chroma, and Milvus. And that's not all we are going to do. We are going to talk about embeddings again. We will build a basic vector index. We will choose the right vector index. We will do some optimization, and we will talk about integrating vector indexing into RAG systems because this is where they come into play, but we will discuss this. And finally, we will do some troubleshooting and common pitfalls. So what you will learn is that you embed your personal knowledge into the model, and this matters because fast scalable search turns raw data into instant answers. Without it, your AI drowns in noise. So why vector indexing exists? The core problem, the limitations of keyword search. Keyword search is lexical, not semantic. So it fails on synonyms and meaning, like feline pet is not equal to cat, and cannot support multi-model search, so images and text. The high-dimensional retrieval problem, AI models produce embeddings, for instance, 384 to 1536 dimensions, and searching millions of these vectors with brute force is simply too slow. So what vector indexing solves, it enables fast semantic search, it supports approximate nearest neighbor or ANN, it reduces search times from hours to milliseconds, and this section sets the problem that vector databases like FAISS, Milvus and Chroma solve. So why LLMs need retrieval or RAG? We discussed RAG in previous chapters a little bit, but this and the next chapter we are going to discuss it a little bit more. LLMs have fixed training knowledge. They cannot know new events and they hallucinate when they don't know. And RAG solves this from query to embedding, search in a vector database, retrieve top K relevant documents and feedback into the LLM as context. Simply said, we can import our own knowledge into the model, so the model knows our knowledge as well. And this helps because this way we can basically combine the knowledge of the model with our own knowledge, and this might give us some nice output. Real-world usage, enterprise documentation, medical and legal knowledge, up-to-date news and internal company data. So this connects vector search to why AI systems depend on vector databases. Embeddings, representations of meaning. So what are embeddings? Well, embeddings, and we did discuss this in long length, if I need to say so, but we discussed this pretty well in previous chapters, but still as a little recap, embeddings are numerical vectors representing semantic meaning and produced by models like Sentence, BERT, OpenAI, Ada, Mistral, Embed, etc. How embeddings encode meaning? Well, similar text reproduces or produces similar vectors. This ambiguation of context, well, bank, finance versus river. Embeddings enable semantic text search, image to text search, cross-language retrieval, and personalized assistance. This is the fundamental object that vector databases manage. And this will become clear in a few slides. Similarity search versus keyword search. Similarity search uses cosine similarity or dot product and finds the nearest vectors, the semantic matches. Keyword search uses TF-IDF and BM25 and relies on textual overlap and not specifically meaning. And why similarity search matters? This retrieves the meaning and not just the words. It handles paraphrases, synonyms, and related IDs and is essential for RAG quality. Hybrid search is a mix of BM25 and vector search, and this is used in a high accuracy RAG systems. After this, you'll understand why vector indexes matter. Here we see a little example. We have a user query and a specific search type. This can be similarity search or keyword search. Similarity search will have a vector match cosine, nearest neighbor, and meaning based, and the output is semantic, but it needs indexing. And eventually for the keyword search, this will use BM25 or inverted index, exact words only. This is fast but semantically blind. And finally, we want hybrid search, which is keyword searching and vector searching. This is where both of them come together. For red teams out there, vector indexes can be poisoned by inserting adversarial embeddings. Test for index pollution by injecting vectors that distort similarity search. RAG pipelines are vulnerable to retrieval manipulation. They are biased, harmful, or irrelevant content. And pen testers probe with synonym and relevance skewing attacks. We can do things with this, and we will see this, of course, when we start pen testing. Cosine explained. Well, since we talk about the cosine term a lot in the previous slide, let's dive into this because we haven't discussed cosine really well. So what is it? Cosine is a function from geometry that measures the angle between two vectors. In vector search, cosine similarity tells you how similar are those two vectors based on the angle between them regardless of their length. Why the angle matters? Well, imagine each embedding as an arrow in multi-dimensional space. Two arrows pointing in the same direction means a very similar meaning. Two arrows pointing at a 90-degree angle is very much unrelated, and two arrows pointing opposite directions have a opposite meaning to each other. Cosine similarity turns this into a numeric score. So the cosine range, cosine produces values between -1 and +1. +1 means vectors point exactly the same way, so this is a perfect match. -1 is where vectors point the opposite directions, and this is an inverse relationship, and 0 means that the vectors are orthogonal, which means basically no relationship. In the previous example, this was the 90-degree angle. In text embeddings, cosine is almost always positive because semantic vectors cluster. Why cosine is preferred in LLMs and RAG systems? Well, it is scale invariant, meaning doesn't depend on vector length. It is stable for high dimensional spaces. Euclidean distance becomes less meaningful in 100 to 4000 dimensions. Well, this is the curse of dimensionality. And it is the best performance on semantic tasks. Research consistently shows that cosine outperforms Euclidean and dot product for text. The formula, which is pretty simplified, cosine similarity uses cosine A and B is the same as A, I think it is explained here as well. Well, this is the dot product, the dot product between A and B, so how much the vectors overlap. The second part is the length or the magnitude of vector A, and the second one is the length of vector B. And this is basically the simple formula. If we normalize vectors so their length is 1, then cosine A and B is equal to the dot product between A and B. And this is why we normalize embeddings for cosine search. This is faster and cleaner. You don't have to remember the formula, you don't have to know exactly what it does, but know what cosine does and how it looks like. And I think in the next slide we have a visual representation as well. Why cosine is used for embeddings? Well, embeddings encode meaning and not magnitude. Two sentences with similar meaning may produce vectors of different length. Cosine ignores the length and focuses only on the orientation or the similarity. For text like car and automobile, which basically mean the same, but looking at the words, they are very different. Their embedding vectors point in the same direction because they mean the same. So cosine will be approximately 1. While car and banana are different things, so the cosine will point in unrelated directions. In this case, cosine is approximately 0, which means no relationship. And here we have a visual intuition, a 2D example. Even if A and B have different lengths, the angle is what matters. A small angle is a high cosine and is similar, and a large angle is a low cosine and is dissimilar. So where do vector databases fit in modern AI systems? Vector databases, for instance like FAISS and Milvus, sit between data ingestion and AI inference, storing embeddings for fast retrieval. In a full pipeline we have some raw data, we have an embedding model, then we have a vector database, then we have query embeddings, then we have retrieval, and then we have the LLM. So they integrate with frameworks like LangChain for RAG, enabling scalable AI applications, and in modern systems they handle multi-model data, supporting Gen AI beyond text. And in the example below we have some raw data like documents, images and audio, and then they enter a embedding model, so vectors are being created of this raw data. Then in the AI retrieval pipeline we will start off with a user query. This query will be embedded as well, so we have a query embedding, and the vector of the raw data and the query embedding they will both reach the vector database FAISS, Milvus or Chroma, where the top K relevant chunks are retrieved. And this is the LLM inference or RAG response, and this all integrates with LangChain and RAG frameworks. But both of the knowledge of the LLM and the vectors of the raw data in a RAG pipeline will be in the LLM and in the vector database. So what are embeddings? First, let's discuss a few core concepts, the dense vector representations. What are dense vectors? Embeddings are arrays of floating point numbers. We know this already. For example, we see a small part of a potential embedding array, and every dimension contributes meaning, unlike sparse vectors with mostly zeros. Dense vectors encode semantic similarity, context, and relationships between concepts. Why dense? Well, compact meaning representation, efficient for similarity search, and captures subtle relationships that sparse bag of words models can't. So dense versus sparse vectors. We have some textual input which will enter a embedding model. See this as a query and this as a query embedding. Then we have dense vectors and we have sparse vectors. Here with dense vectors we have semantic meaning encoded, and with sparse vector we will have mostly zeros, which is term frequency based. And as you can see, the dense vectors can use minus, they also can use dot representations, where sparse simply can't. Another core concept in this is dimensionality. We already discussed this a little bit. Well, embedding dimensionality, typical dimensions like 384, which is a mini LM, fast and lightweight, and a larger one, the 1024 to 4096, is a large embedding model, which is simply more expensive. But in the end, it can hold more intelligence. Higher dimensions capture more nuance and require more compute, like RAM and storage. Dimensionality reduction. We can reduce the dimensionality with techniques like PCA, SVD, and autoencoders. And the goal here is to reduce dimensions without major loss in meaning. The benefit, if we will reduce, then we will have a faster search, smaller indexes, and thus less compute, RAM, and storage. So cosine versus inner product versus Euclidean. Cosine similarity, we already have seen this formula. This measures the angle and not the magnitude, and this is best for text embeddings. Magnitude often irrelevant. Inner product, where a formula is a dot b, which is equivalent to cosine when vectors are normalized. Then Euclidean distance, where the formula is different, where we have the square root of a minus b to the power of 2. This one measures geometric distance and is sensitive to vector scale. So what we have thought up until now is how embeddings turn meaning into geometry, where similarity metrics decide how we measure closeness in that geometry. So we actually learn these things to know how embeddings represent meaning geometrically, how similarity is mathematically computed, and why metric choice affects retrieval results. And then again, why vector search engines behave differently. This is what we will see in a few slides from now. But it is important to know that there are different kinds of metrics for different kinds of purposes, and we need to be able to choose the right metric. So cosine similarity for semantic search, inner product for normalized vectors, and Euclidean for clustering or geometry-based tasks, which is basically what we see in the graph on the right. For the red teams, attackers can manipulate vector norms. This will fool similarity threshold, and this will bypass naive embedding-based access controls. Keep this in mind. Once you get to know how some things are computed and which methods are being used, this can become important. Another one of the core concepts, why embeddings capture context. We have distributional semantics, where embeddings learn the meaning from co-occurrent patterns, and words and phrases appearing in similar contexts mean similar vectors. And this enables context-aware search, semantic clustering, robustness to synonyms, and paraphrasing. So the graph on the right, we have large training corpus, then we have co-occurrent patterns, we have model learned context, which is the third step. Then we have an embedding space where words in similar context have close vectors, like bank finance is not equal to bank river, but bank and finance are close to each other. And on the other hand, where meaning is encoded by positions. So create text embeddings. Here we see a small Python-based example of how to do this. And another one of the examples here, where we say we use the model AL mini LM L6 V2, and we have the following text. This is a sample sentence. Embeddings capture meaning. And then next we print the embeddings, and we print only the first 5 dimensions of them. which are those, and here we can see which things are close to each other, and primarily the first two ones are pretty close to each other. The third one is not. The fourth one is, well, probably does not mean exactly the same, but it's close. And the later one is not so close to the first ones. But we can visualize all of the embeddings and see if the meaning is the same or a little bit different. Key takeaways is to use a pre-trained model like MiniLM, which is fast and has a good quality. And the output is a dense vector per text block. This is what we see here. And the shape tells you numbers of items multiplied by the embeddings dimension. But still, this is all very mathematically not that important. The key takeaway in my eyes is that you can visualize embeddings, you can see how close they are to each other, and we have different methods of calculating them. Practical skills, chunking strategies for documents. So now we are going to talk about raw documents. Why would we chunk documents? Well, embeddings handle approximately 200 to 512 tokens, and documents must be split into manageable text blocks because documents contain a lot of content and a lot of text. There are different kinds of strategies: the fixed size chunks, semantic chunks, and overlap chunks. Fixed size chunks are chunks of 512 tokens, or at least of a predefined set of tokens. Semantic chunks are chunks based on items in the documents, like paragraphs, headings, or sentences. And we can use overlap chunks like 10 to 20% to preserve context. So we need overlap chunks to preserve some kind of context. Let's say if we have semantic chunks where we use sentences as chunks, then we want to overlap one sentence to each other to still know the meaning that they have to each other. Bad chunking causes are fragmented meaning, poor retrieval, and the loss of context for an LLM. If we do this, then it is wrong and we are doing something wrong and we need to change our way of chunking. In the graph, we have a raw document. We will choose a chunking strategy, for instance, the fixed token size with 512 tokens, and this gives us balanced sizes and simple logic. If you would use semantic chunks, for instance, sentences and paragraphs, this will keep the context coherent. And if we work with overlapping chunks, then this prevents context loss around the boundaries. For red teams, attackers can inject malicious text at chunk boundaries to break retrieval and bury or distort sensitive content. Storing metadata with embeddings. Why metadata for embeddings matter? Metadata makes vectors searchable and filterable. And metadata can be something like the source URL, timestamps, document type, and access or permission tags. For best practices, store embeddings and its metadata as key value pairs. Use namespaces or collections for grouping and filter by metadata before running a similarity search. So we have a chunk of text, then we have a specific embedding model, which will create a kind of vector, and we will store this in a vector database. We will store the embedding and we will store the metadata like URL, timestamp, and permissions. And this is this way we can filter search by metadata, and in the end the embeddings will give us a similarity search. So evaluating embedding quality, because it's important that we can evaluate the quality to know if our embedding strategy works. So how to evaluate embeddings: to use semantic textual similarity or STS benchmarks, cluster quality on purity and silhouette score, domain-specific test, similar Q&A, question and answering pairs, and document similarity within your field. As a practical rule, if results looks noisy or unrelated, your embedding model is wrong for your domain. So here we see the embeddings. We have an intrinsic evaluation and an extrinsic evaluation. For intrinsic evaluations, we have STS benchmarks and clustering quality, purity, and silhouette. And extrinsic evaluation has domain-specific test and retrieval accuracy of RAG. And then we will say or check if documents that are retrieved, if they are similar or if they are not. In-memory storage, and this is where the vectors live. The core idea here is that for small projects or demos, you don't need huge vector databases like FAISS or Milvus. You can simply store the embeddings that it created directly into memory. And how to store this? To store this, we can use NumPy arrays to store dense vectors. And here you see a little example of how to create a specific array. Keep parallel lists for IDs, metadata, etc. All the things we just discussed, which we need to save together with the vectors. And this is suitable for, well, approximately like 50,000 embeddings or a little less. For instance, for prototyping and debugging. Exact versus approximate search. Where there is a vector database available, you'll have different search methods to retrieve the correct data. We have exact search, which compares query with every vector, which is 100% accurate, which has a specific cost per query, and it is good for small data sets. We have another thing that is the simplest nearest neighbor search. And once the dataset grows large, like more than 100,000 vectors, exact search becomes too slow. And then you'll switch to ANN, an approximate nearest neighbor method. And we have different methods. For instance, KNN, the K nearest neighbors, FAISS, IVF, HNSW, and like another two that we are going to discuss are Milvus indexing and Chroma with HNSW. ANN builds specialized indexes that trade a little accuracy for massive speed improvements. ANN is how you will get 10 to 1,000 times faster search, near real-time retrieval, and this gives you support for millions to billions of vectors. So really large vector databases. So let's start about building a basic vector index based on the simple nearest neighbor search. And the most simple way to query a vector index is by using the basic KNN with cosine similarity, which will normalize the embeddings, compute cosine similarity within the query, then it will sort all the results, and finally it will return all the top K results to the user. And here we have a minimum search engine example code. This is, well, I guess it's complete, but it is very, very basic. We will see another version of this, a little bit more complete later on. We will have some trade-offs like latency versus accuracy. Latency is that we have a lower latency, which means that we will have faster queries. And the use here is to approximate search, optimized indexes, and quantization. But for accuracy, with a higher accuracy, we will have a closer to perfect nearest neighbors, which we'll use in exact search and higher recall AANs. So we need to find a balance between these two. And for instance, for a real-time chatbot, we need to prioritize latency. For compliance and safety checks, we need to prioritize accuracy, because here speed is less important than the quality. And for a recommendation system, we need to use a high recall AAN, which has basically both of them. For red teams, approximate search can be gamed. Attackers can craft vectors that sit near enough to bypass filters. And here we have a hands-on to build a minimal index example, where the goal is to create a simple in-memory index using NumPy, and we do this in different steps. We'll start by storing the embeddings in a NumPy array. Then we normalize them for cosine. We store metadata, the IDs, the sources, etc. We implement a brute force KNN search, and we package the functions into insert query and top K, which you will see if we look at the original code. We have a simple vector index. This is the insert function. We have here cosine similarity, the query function, the brute force KNN. And here we have the top k indices only, which will be returned. This is the demo usage, and we will print everything. So let's try this as well. You'll see the example here. So everything is printed. It will build different kinds of, well, let's say documents. We have document ID 9, which goes by this specific name. And it has all of those elements. So this is a specific array, and then it will check the top 3 matches of all of these arrays. And you will see that the scores of these 3 arrays are pretty much alike, meaning a similar meaning. Document 6, 8, and 5. If we run it again, it's different. It's documents 2, 5, and 7. But just to show you on how this simple method works, the minimum index. Here we have another hands-on to insert or append embeddings. Inserting embeddings means adding new vectors into an existing vector index or vector database. So let's say we already have a few arrays, an embeddings array with existing vectors and an IDs array with existing IDs. Then inserting means that we will have to add a new vector to the embeddings, add a new ID or / metadata to match it, and update the index. And the naive approach is the following, where we have embeddings with an NP and NumPy v stack. And we stack a new embedding and a new vector, and we append everything with a new ID. But this approach is slow. Now, why is this slow? NP vstack creates a brand new array every time. It copies all the existing vectors from the old array into the new one, and runtime grows with the number of vectors, copying at each insert. And this is fine for a few thousand vectors, but terrible for millions. Real vector databases like FAISS, Milvus, Chroma, Weaviate avoid this by using optimized memory layouts and batching. So better approaches: pre-allocate matrix capability, where embeddings is equal to NP zeros 1,384, D type is NP float 32. Well, this doesn't say anything, but this is just the method on how to do this. We can use dynamic structures like Python lists. We can use memory mapped arrays with mmap, and we can periodically rebuild the index. Here we'll have a script that does it the old way, so the naive approach. This is simple but slow, and I guess we have another example as well. This is the old method, which you can see in action here as well. Let's clear the screen and let's do a Python append embeddings naive approach. And here we have some new IDs and a new shape. And the outcome is the same every time because this is built pretty statically. The new ID is 5, and it will print the new shape and the new ID. So we have 0 to 4, and we will add number 5. Just to show you the simple approach. And in the end, we will have 0 to 5. Now we can also create a script that uses a better method, and this script uses a dynamic list structure, and this is flexible and simple. And as you can see, the code is a little bit bigger, but not that much. So we create 2 empty arrays, an embedding list and a meta list, and we will insert 10 vectors down here. And this will look, if we go to here, this will look like this. And surely because those vector arrays are so small, you don't see the difference in speed already. But when you have more than, let's say, 100,000 to 1 million vectors, the speed difference is absolutely noticeable. So query and rank results. Well, the goal here is to show how simple vector index answers a query using cosine similarity. We have a specific pipeline for this. First, we encode the query, we convert the text to embeddings, then we will normalize everything to a unit length vector. We will use similarity computation. And for this, we use cosine similarity against all stored embeddings. Then we will rank descending, so the highest similarity is the most relevant, and we will return the top k vectors, the scores and its metadata. And the key insight here is that this is a pure exact search, so a brute force KNN. And everything that we just said is in the graph below. So let's reinforce some concepts. Let's take another look at cosine similarity, which measures the angle between the vectors. We already know this, and this works best for semantic embeddings. That is something you already knew. So again, the formula where similarity equals a dot b divided by the norm of a times the norm of b. Then normalization, we convert the vectors to unit lengths. That's what we do there. And this makes cosine similarity easier and numerically stable. And KNN ranking is where we compute similarity scores to all vectors. Then we sort them and we take the top X items of this. Accuracy of KNN, where we have a brute force, which is 100% accurate. And the approximate methods like FAISS, HNSW, and Milvus, they trade accuracy for speed later on. But still, again, the accuracy is pretty well. Now you will build a fully working in-memory vector index, a full brute force exact KNN, full cosine similarity ranking, full metadata return, and a functioning semantic search engine. And if possible, try this with under 50 lines of code. And this matters because this is the foundation of RAG, of retrieval augmented generation, of semantic search, document QA, recommendation systems, and image, audio, and multi-model retrieval. Every FAISS, Milvus, or Chroma system uses this exact pipeline under the hood, just massively optimized. And in the end, your code will look something like this. So add your own custom demo data, you can see the screenshot below, and define your own question. And I simply took this example, the basic vector index. And this isn't under 50 lines, but still we have a lot of comments here, which we can remove to do this with less than 50 lines. So we will load the embedding model, in this case MiniLM L6 V2. Then we have the stored data, where this example document ML Finance contains the text machine learning for finance. The second one, bread recipe, is how to bake sourdough bread, etc. So this is our data. We will encode all the stored documents, normalize each embedding for cosine search, and then we have the query function, which is the core of the basic query pipeline. So we will convert the query text to embeddings, we will normalize, we compute cosine similarity, then we will rank descending and return the top k numbers. And then our example query that we will run against this data is explain neural networks. And in the end, this will look like this, and this might take a few seconds. So the biggest match is this document, neural networks and deep learning, which has ID number 2, and which is the deep learning document. And the second one that matches, although it's a lot lower, is the machine learning for finance in the ML Finance documentation. Now let's change our question to how to bake sourdough. And sure, now the best document with the highest match is the bread recipe. And the second one, which is a lot lower, is the deep learning document. So this is absolutely the best one by far. And this is how simple that it works. So you can do this as well, because this is basically your task to do. And after this, after we have the basics in play, we can discuss the different optimizations. And we'll start with FAISS. And FAISS exists Why FAISS exists? Well, FAISS is Facebook AI Similarity Search, and this is a high-performance library built by Meta AI for fast vector similarity search at massive scale. And this exists because traditional brute force search becomes impossible at millions or billions of vectors, and FAISS provides optimized GPU-accelerated data structures for fast nearest neighbor search. It is designed for production workloads such as recommendation systems, semantic search, multi-model retrieval, and RAG at scale. The key idea of FAISS is to make similarity search fast, scalable, and memory efficient. The industry standard for high-performance search, well, FAISS is widely used in industry because it's developed and battle-tested inside Meta. It is highly optimized C++ core with a Python bindings. It supports all major similarity metrics like L2 or Euclidean, inner product, cosine similarity through normalized vectors, and it has a built-in support for both exact and approximate searches. FAISS is the default recommendation for systems requiring speed, scalability, and accuracy. GPU acceleration, and why it matters? Well, FAISS offers CUDA-based GPU acceleration, enabling 10 to 20 times faster search and index building, efficient handling of millions of queries per second, seamless transfer between CPU and GPU modes. GPU acceleration is critical when indexes contain more than 100 million vectors, where real-time systems need less than 10 milliseconds retrieval, and recomputation or reindexing must be very fast. So FAISS is built for extremely large-scale deployment. FAISS is engineered to handle billion-scale datasets. Capabilities of FAISS include memory-efficient quantization, partitioning strategies, IVF for fast lookups, out-of-core techniques that avoid running out of RAM, and GPU sharding across multiple cards. For red teams, large-scale FAISS installations can be targeted through query floods, causing delayed responses or resource exhaustion. Test scaling limits to prevent denial of service. This is one thing we as a red teamer can do. The key concept for FAISS are flat indexes, and index flat is FAISS' simplest index type. It performs exact search, it has no compression and no partitioning, it has the highest accuracy, and it is the slowest at large scale, but still doable. This is used for baseline benchmarks, small data sets with less than 1 million vectors, and for evaluating approximate indexes for accuracy drop. IVF, inverted file index. IVF partition vectors space into clusters, and we call those clusters cells. FAISS learns centroids through k-means. Each vector is assigned to its nearest centroid, and at every time FAISS searches only for the most relevant clusters, controlled by nprobe. The benefit of this is a massive speed up and a tunable recall versus latency. The trade-off here is that it requires training and it is slightly slower. It has a slightly lower accuracy than flat, the example we've seen in the previous slides. And then we have product quantization, or PQ, and PQ compresses vectors dramatically. So from 1024 bytes to 16 bytes, that is a huge compression. And this works by splitting vectors into subvectors and quantize each subvector with codebooks. Then we store compact codes instead of floats. The benefits are that indexes billions of vectors into the RAM and faster search due to smaller memory footprints. Also, here we have a few trade-offs, like it is an approximate search with a lower precision compared to uncompressed indexes. HNSW. The key concept of HNSW integration, well, FAISS integrates the HNSW graph algorithm, and this builds a multi-layer navigatable small world graph. It enables very fast approximate search, it has excellent recall even with large data sets, and it's comparable to state-of-the-art ANN systems like Milvus and Vespa. This is best suited for high recall needs, complex ranking tasks, and large but not billion scale indexes. Index training for IVF and PQ. Some FAISS indexes must learn structure from the data, because that's exactly what we said before. These methods require training. IVF training, train k-means on sample vectors to create centroids, and this is required before adding data. And PQ learning, learn quantization codebooks for compressing vectors. Both require index train, in this case, the vectors that need to be trained. The rule of thumb here is that it use a 10 times dimensionality as a minimum training sample size. Saving and loading indexes. FAISS indexes can be persisted with FAISS write and FAISS read. So we can write the index and then we can read the index. And this matters so we don't have to rebuild indexes at a power drop or at a later time. Once it is built, we can reuse them. It supports pre-computed indexes in production, and it enables sharing between environments. And then we have CPU versus GPU modes. We can convert CPU indexes to GPU, and we do this in this specific method where we build a GPU index and we call the method FAISS index CPU to GPU to rebuild it, and we can convert it back with the FAISS index GPU to CPU function. So we can use GPU for fast searches and CPU for persistence or batch workloads. Now, for performance optimization, nprobe is the main tunable parameter for IVF indexes. We have to define the number of clusters to search. If we define a higher number of clusters, this means a better recall, but it's slower. And of course, when we define a lower number of clusters, this is faster but less accurate. Some typical values is where we set nprobe to 10, which is the balanced way to use nprobe. But if you want nprobe to be very fast, then we can set it to 1. And if you want nprobe to have a high recall, then will set it higher than 10. So depending on your preference, we can set it between 50 and 200. For red teams, attackers may use FAISS themselves to test how your RAG system behaves with adversarial indexes, so use FAISS for proactive testing. Don't forget this. This is a hands-on to build your very first FAISS index, and we have an example of this as well. And this is number 5, so let's run Python. You'll see how quick this was. Well, this again has less data, but it is pretty quick, and it basically outputs the arrays of data immediately. So let's get back to the slide and now start discussing Chroma. So why Chroma? Chroma is Python native, and it's a vector database designed to simplify handling embeddings. This is perfect for rapid prototyping or retrieval augmented generation RAG systems, and it eliminates the need for complex setups and external database management. Why it matters? Embeddings are meaningless without fast storage and retrieval, and Chroma handles this efficiently for small to medium scale projects. It's developer friendly, it has a minimal setup, it is installable through pip, and it runs locally, so no server or cluster is required for small projects. Developers can focus on embedding generation and search logic and not on infrastructure. As a use case example, quickly test semantic search over a set of documents without setting up FAISS or Milvus. It is way simpler. Zero configuration options. It supports in-memory mode for environmental experiments. It supports persistent mode with a SQLite backend for projects needing durable storage. Flexibility lets you start small and scale as your project grows, and real-world benefits are that prototypes can immediately transit to production without rewriting code. Built for RAG applications, Chroma stores embeddings for fast semantic search, which is crucial for feeding LLMs relevant context. It works seamlessly with embeddings from models like BERT, MiniLM and OpenAI embeddings, and it integrates easily with LangChain and Llama Index. The purpose is that it enables retrieval pipelines to feed top K results into an LLM context window. And as a benefit, it scales RAG systems across large datasets while maintaining fast and accurate retrieval. For red teams, because of its simplicity, you can quickly build mock RAG pipelines to test retrieval vulnerabilities. The key concepts of Chroma are collections, and collections are a logical container for embeddings and metadata similar to a table in a database, and each collection can hold documents, their raw text, embeddings, vector representations, and metadata like tags, source, and timestamps. Collections organize data for easier querying and filtering. Another key concept is metadata and filtering. Well, metadata tags each vector with contextual information. Some examples: document type, owner, or sensitivity level. Queries can filter results based on metadata, for example, retrieve only documents from a specific source, and this makes semantic search precise and avoids irrelevant results. Then Chroma knows some persistence modes. Of course, we have in memory, which is fast but temporary and which is good for testing and experimenting. And we have the persistent client mode, which saves embeddings and metadata to disk in a SQL-like structure. And this survives restarts and is thus more persistent. Real-world benefits: it supports production RAG systems where you need stable, durable, and knowledge stores. So for in this specific matter, persistent client is the best option. Practical skills: creating a collection. Well, here we have an example of how we create a collection. We initialize the Chroma client and we create a collection for embeddings with client create collection. Simple as that. Explanation: well, I already did. In the first steps, we connect to Chroma, which is in memory or persistence. This is something we can choose. And in the second step, we define where all embeddings and metadata will live. Why? Well, collections are the building block for storing vectors, and an LLM will query those collections later on. Then adding documents and embeddings. Well, we can add documents with a collection add function, where each document gets a vector representation. The ID is used for retrieval and reference, and without this, the LLM cannot access contextual information or accurate RAG responses. So here we have the documents. In this case, it is just a piece of text. We have the embeddings, and then we have a specific ID, and something like this we have seen in the previous practical example. Then we can query it with filters, where we have query text is a search text and where category equals finance, and this is an optional filter. So this returns the top K most similar embeddings, and filters allow queries to target specific subsets of your knowledge base. This combines semantic similarity and metadata-based precision for better retrieval. Then persisting a Chroma database. We have the Chroma DB persistent client function. And well, this way we store our embeddings and metadata to disk for long-term use. This ensures queries work consistently after restarts or system failures, and this is essential for production RAG systems where ephemeral storage is insufficient. And down here we have another Chroma database hands-on demo. So let's get the code, and this is basically the demo that we wrote, or that we can write. First, we initialize the Chroma client. We will create a collection with client create collection, exactly as we did in the slides before. We will load an embedding model. We will use MiniLM L6. Then we will prepare some documents, 3 documents in this matter, document 1, document 2, and document 3, containing the content. Chroma is a Python native vector database. Vector embeddings allow semantic search, and RAG systems use retrieval augmented generation. We will convert the documents to embeddings. We will store the embeddings in Chroma, and we do this in memory. And once this is done, we will see that the documents successfully are stored in the vector database. We will create a specific query, and then Chroma will do its job and searches through the vectors and returns all the documents. In this case, 2 of them that are the most fitting to answer our question. So our question was, how does semantic search work? Now let's go back to our code. and it will take a few seconds to run. And answering this question, we will have two top matching documents. First off, there's document 2 and next is document 3. Now let's change our question. Where is our Visual Studio Code? Right, we do have Chroma is a Python native vector database and RAG systems use retrieval augment. Okay, so we will change to what do RAG systems use? And now we will rerun the code and we will probably get some different results. And if all went well, we will get document 3 as first, which we do. This is probably the document most matching the answer to our question. And second is document 1, where Chroma is a Python native vector database. But this is a nice example of using Chroma. And this shows the outcome of the query, which we just did see. Then there is something else, and this one is Milvus. And Milvus is designed for massive scale vector search beyond single machine limits. It handles billions of embeddings efficiently, making it ideal for enterprise AI and RAG. This is optimized for low latency queries and high throughput, and it enables scalable AI applications where traditional databases fail. We have a cloud native and distributed. Well, Milvus is Kubernetes ready, supporting modern cloud deployment patterns. It is built for distributed clusters, and vectors can be spread across multiple nodes for resilience and performance. It integrates with Python with the PyMilvus module and AI pipelines for seamless LLM retrieval. Milvus has petabyte scale capability. It can manage petabytes of vectors across multiple machines, which is ideal for applications like recommendation engines, search, and multimodal AI. It has a high throughput and horizontal scaling. Milvus allows adding nodes to increase throughput. It supports parallel queries, enabling real-time retrieval even with billions of vectors. Horizontal scaling ensures performance grows with data, which is crucial for enterprise-grade AI applications. Talking about collections and partitions, collections are logical groupings of vectors and each can have its own schema and metadata. Partitions with Milvus are subsets of a collection used to improve query speed and manage data access. As a use case, we can have organizing vectors by data type or source, for instance, text versus image embeddings. We have different index types. We have IVF or inverted file. Partitions the vector space into cells, searches only the nearest cells, and this is faster than the approximate search. We have again HNSW, which is a hierarchical navigatable small world. And this is a graph-based structure for fast nearest neighbor search. We have diskn, which is optimized for disk backend retrieval, and this is useful for very large data sets. So choose the index type based on accuracy requirements, dataset size, and speed. Here we do a little comparison between a Milvus server versus a Zillis cloud. Milvus server is self-hosted, complete control over the infrastructure, indexing, and its security. And Zillis Cloud is a managed service. It automatically handles scaling, replication, and maintenance. And the decision here depends on IT resources, security policies, expected load, and also the type of data you are working with. So we can quickly start with Milvus when we do the deployment in Docker. And this is a production-ready deployment through Kubernetes. It can integrate with RAG pipelines to provide vector retrieval for LLMs, and it is just as simple as running a Docker container. In this case, it's the Milvus DB Milvus latest, so the latest variant of it. And we will open up the specific ports. We will map port 19,530 to our port, which is the same. So we can access this specific port inside the Docker container. Inserting and indexing embeddings. Insert vectors using the Python client, again by Milvus. Connect to the Milvus server, create a collection and insert embeddings along with metadata like IDs, timestamp and sources. Then create indexes to optimize the query speed, and index type selection impacts the trade-off between accuracy and speed, as we see the same trade-off time and time again. Query in vectors. Support this again supports top case similarity searches across billions of vectors. Query parameters like metric type and search budget control speed versus accuracy, and it retrieves relevant embeddings efficiently for downstream AI tasks like contextual input for LLMs. Tuning and production hardening tune index parameters like M in, H, and SW to optimize performance and use replicas for fault tolerance and backups for disaster recovery. For red teams, distributed replication can create subtle inconsistencies, so test for potential retrieval flaws. Again, something we can test for. Data volume. Consider the size of your embedding data set from MB to petabyte. Small data sets will be ranging from MBs to gigabytes, and here Chroma is sufficient, easy to use locally and in memory, but for large data sets like from terabytes to petabytes, this is where Milvus handles distributed massive scale storage. Large datasets need distributed systems to keep query times low and prevent memory bottlenecks. For latency requirements, sub-millisecond retrieval needed, then FAISS with GPU acceleration provides the fastest queries. Chroma or Milvus may have slightly higher latency depending on the dataset size and configuration. So use case examples, real-time recommendation engines or chat applications require low latency vector search. And again, FAISS might be a very good option to use here. Hardware availability, GPU available, then FAISS can fully leverage CUDA for speed. Cloud deployment, well, Milvus offers scalable distributed vector searches in the cloud. And Chroma is lightweight and works on CPU-only environments, making it ideal for local testing or prototyping. And you also have to consider your budget. Open source solutions like Chroma, FAISS, Milvus, and then the self-hosted variants. We have managed services like the Zillis Cloud offering operational convenience at a cost, and always budget impacts the choice of system, free and flexible versus paid but fully managed and scalable. And the architecture is something else we have to take in consideration. Local applications like desktop applications and small scale prototypes. Here in this case, Chroma might be the best choice. Cloud or distributed systems, enterprise AI, multi-node LLM pipelines, then here we will take a look at Milvus. So consider architecture to ensure compatibility, maintainability, and scaling. And for a little decision graph, we have this graph. Start a choosing index, vector index. First off, we have to take a look at the data volume. Do we have small or do we have large data sets? Let's say we have a small data set, then we need to think about the latency. So if we need sub-millisecond latency, then we might need a GPU and then we can use FAISS. But if we don't need this, then and we are building a local application or a prototype, then Chroma might be the best thing to use. So this is a nice decision graph on how to choose the right technique. So choosing the correct index type, different indexes suit different workloads. HNSW, hierarchical navigatable small world, is a very fast approximate nearest neighbor search and good for low latency queries. IVF, the inverted file index, balances speed for accuracy, partitions vectors into cells for more efficient search. Tip, match the index type to your query patterns and dataset size. Then for dimensional reduction, high dimensional embeddings increase compute and memory cost. We have a few techniques here like PCA and L2 normalization. PCA, the principal component analysis. This is a reduced vector and this reduces dimensions while preserving most variance. L2 normalization, scale vectors to unit lengths, and this is necessary for cosine similarity comparisons. As a benefit, faster search, reduced memory, and this preserves semantic relationships. And again, quantization, compress vectors to save memory and speed up searches. PQ, product quantization, split vectors into subspaces and encode as centroids. OPQ, the optimized product quantization, rotation before PQ to reduce reconstruction errors. We can use int or float 16, so we will reduce the storage without major accuracy loss. As a trade-off, a minor decrease in similarity precision versus large gains in memory and speed. But we did discuss this once, I thought it was the previous chapter where we did discuss quantizations. We also have caching strategies. Frequently queried vectors can be cached to reduce computation. And for this we can use LRU, the least recently used cache, and this keeps the top queries in memory. As an impact, it reduces query latency and it improves the user's experience. So caching might be a good method to do. Hybrid searches combine traditional keyword search with vector similarity for best results. As an example, BM25 plus embeddings re-ranking. First retrieve by keywords and then rank by semantic similarity. As a benefit, it handles edge cases where embeddings alone may miss relevant matches. Handling stale and or updated documents. Vector indexes can become outdated as documents change. And for this we have a few different strategies like versioning and reindexing. Versioning is where we keep track of the vector updates, and reindexing is where we periodically rebuild indexes with new or updated vectors. So our index will be updated as well. Red teams, attackers can exploit stale indexes by injecting outdated or adversarial documents to manipulate search results. And here another graph. The start is a vector index optimization. So we have to choose the correct index type, HNS-W or IVF. We have to think about dimensionality reduction, PCA to reduce dimensions, and L2 normalization for cosine similarity. We also have to think about quantization, PQ, OPQ, or int or float 16 compressions. Then caching strategies is something we can think of like LRU cache for frequent queries. Maybe we can use hybrid searches, a keyword search with BM25 or embedding similarity re-ranking. And finally, we have to handle stale or updated documents somehow, so we can do this with versioning vectors or simply by re-indexing periodically. All things we have to reconsider. The pipeline overview, vector indexing in RAG systems, and we will talk about this in the next chapter as well. For the flow we have data ingestion, then we have chunking and embedding, indexing, retrieving, then the LLM comes into play, and all of these together will form a response. As the purpose of this is to efficiently connect raw data to LLM reasoning through vector retrieval. And this has, of course, benefits. It reduces hallucinations by grounding LLM output in real data. And not only real data, but also sector-specific data, or at least data from your own environment, to tell the LLM what is real, what is not real, and what to keep in mind while thinking about an answer. And here we have basically the same thing. So at phase 1, we have some data ingestion, chunking and embedding. And then we have a vector index storage. And with the vector index storage, we will have a user query. That query will be embedded. And then that query will retrieve data from the vector index. Once this data is retrieved, then the LLM reasoning with context, and the context is the information that is retrieved from the index, will take place and will form a response. Data ingestion. Well, we have to put data inside the vector database. Load documents from multiple sources like PDFs, HTML, logs, websites, etc. Then we have to clean and normalize its content, so we have to remove the noise and irrelevant sections. And the goal here is to provide high quality data for embedding and retrieval. Chunking and embedding split documents into manageable pieces like tokens, sentences, and paragraphs. Embed each chunk into a dense vector with using models like MiniLM or BERT, and overlap chunks to preserve context. Ensure semantic search works efficiently. We have to deal with index storage. We have to choose the appropriate vector database. For small scale, well, Chroma, local and in memory. And for large scale, we can use Milvus or FAISS. Although FAISS can be used at small scale as well, but it's up to some different decisions. We have to store embeddings along with metadata for filtering, and we have to consider persistence, replication, and update strategies. Retrieval of data: when a user submits a query, encode it into a vector. Perform a top K similarity search in the index. Optionally, we can apply metadata filters to narrow their results. And as a goal, we have to retrieve the most relevant context for the LLM. Then the LLM will start reasoning with the retrieved context. So feed retrieved chunks as additional context to the LLM prompt. As an example prompt, based on the following context, answer the question. And the benefit here is that it increases factual accuracy and reduces hallucinations. And once we have an answer, we have to evaluate if that answer is correct. So use RAG-specific metrics like RAG-S, precision at K, and recall at K to measure relevance of the retrieved chunks and quality of the LLM output. For my fellow red teamers, the pipeline is an attack surface, so manipulating retrieval can induce hallucinations. Which was actually not something you want when you use vectors, because you are using all those vectors and internal information to reduce hallucination. So if we can find a way to induce hallucinations, this is a finding of a pen tester. Retrieval augmented prompting. So craft prompts that explicitly reference retrieved context, for example, using the provided context, explain, and this improves LLM reliability and interpretability. Evaluating retrieval relevances. Compute cosine similarity between query and the retrieved chunks, set thresholds to filter low relevant results, and ensures that LLM receives only meaningful context and works with this specific context. We have to mitigate hallucinations through retrieval, so always ground LLM answers on retrieved facts. Use top K chunks and avoid empty or low similarity results, and prevents generation of fabricated information. So to build a retrieval chain, combine multiple vector indexes and retrieval steps. Use frameworks like LangChain to create end-to-end retrieval augmented pipelines. And this enables modular, scalable RAG applications. So then we are going to build a Python example demonstrating the core RAG principle using vector embeddings and in-memory similarity search. So the code you are going to see, the core principles here are embedding the knowledge base. So we have to convert all documents into dense vectors so that semantic meaning is captured numerically. Embedding the query, we will convert the user query into a vector in the same space. Then we will do a similarity search where we compute cosine similarity to find which documents are the closest in meaning. And then we will retrieve the top K documents. So we select the most relevant context and we will feed this to the LLM or the RAG. At this case, it is basically a RAG. So use the retrieved documents to generate a grounded response, reducing hallucinations. Make sure you can work with dynamic queries or user prompts, so not make it statically like in the previous examples. Here we do have an example which we will see in a second. Well, let's do this right now. So this is its code, and we have seen this structure before. We will load a pre-trained model. Again, MediaLM, we will create 4 documents in this case, document 1 through document 4. We will take the top K results, 2 of them, and then we will simply allow a query and to return some document that is closest in meaning. And again, we are doing this in a manual in-memory vector search by using NumPy. So this is basically a demo to a real vector index, but still not an indexing technique that we discussed in the latest slide. So one of the 3, like Milvus, Chroma, and FAISS. But as an example, let's try this one out. Let's clear this up. And now let's do Python integrate vector indexing into a RAG system. So we can ask it something, giving the input, let's say, which databases enable fast semantic search. So which databases enable fast semantic search? And of course we have first document number 3, vector databases enable fast semantic search, and document 4, LangChain helps integrate LLMs with retrieval pipelines. But this score is way lower than this similarity score, so this one ranks the best. We can change this a little bit if we wanted it to. Let's see. And this is the important part. Here we will compute cosine similarity. So in this case, for each query, we will compare against every document. Then we will find the documents. And this is just fine for like 10 documents, but this will become bad for like 100,000 or a million documents. So we can change this to a FAISS example again. And then it will look something like this. And you'll see that here we will perform an index search. So this is something completely different. Instead of computing a similarity against every vector manually, here now we will use a FAISS index. So when we use more than like 100,000 documents, brute forcing like we did before will become slow. And as we learned, FAISS provides optimized C++ backends, a GPU acceleration, and an approximate nearest neighbor search. So if you are building a RAG system that needs fast retrieval, like less than 50 milliseconds, then you will need scalable indexing, efficient memory usage, and this is absolutely something that FAISS can provide. And as an example, you can think about a chat that needs to search to 500,000 PDFs at once and answer the user. Enterprise searches, threat intelligence, vector stores, SOC document retrievals, and other large knowledge bases. So let's run this one as well. And again, we can enter our query and we have basically the same for documents. So let's ask, what is a popular programming language? What is a popular programming language? And of course, the first document is the best one. Python is a popular programming language. And second in place with a much lower score is document number 4, where LangChain helps integrate LLMs with retrieval pipelines. But the big difference is that basically we do the same, but we do it much more optimized in the second demo, where we do use FAISS. And again, yes, this is a different Python module that you'll need to install. So if you haven't already, you can do a pip install FAISS-CPU. And sometimes you also have a FAISS-GPU available. So if you have a GPU that you can use, a CUDA GPU or a NVIDIA GPU, then installing the FAISS-GPU is the best option, of course. Now let's continue with the last few slides. Retrieval, which we just did. When a user submits a query, we will encode it into a vector. We will perform a top case similarity search. Optionally, I think we have seen this slide before. This is exactly what we did. We can apply metadata filters, which we didn't, and we will retrieve the most relevant context for the LLM. LLM reasoning with retrieved context, well, feed retrieved chunks as additional context to the LLM prompt. Example prompt based on the following context answer the question. Yes, we did have seen this slide before. It's interesting since it's here again. And we have to evaluate all the things. Bad chunk sizes. Did we do this? We didn't do this, I guess. So bad chunk sizes, this is a problem. This is part of troubleshooting. Choosing the wrong chunk size affects retrieval quality. So if the chunk size is too small, then chunks will lose their important context and the LLM may get fragmented information. So it has a hard time making it the right decision. And if chunks are too large, then chunks include too much irrelevant information. And then this is a noisy retrieval. And again, the LLM will struggle to get the best information for you. As a recommendation, use 512 to 1024 tokens as a guideline. Consider 20% overlap between chunks. Poor embeddings means irrelevant results. Embeddings that do not capture domain knowledge produce unrelated search results. As a solution, we can use domain-specific embedding models and fine-tune embeddings on your specific dataset if necessary. For an example, for medical documents, a generic embedding model may retrieve unrelevant financial text and information. If indexes are not trained correctly, then index structures like IVF require training. Using untrained centroids leads to poor nearest neighbor retrieval. Solution: train indexes on representative samples before adding vectors. As another tip, periodically retrain as data evolves to maintain accuracy. If we have unbalanced partitions, then in distributed or partitionized indexes, uneven data distribution can slow queries or skew results. For the solution, monitor and rebalance partitions regularly, and the effect is that balanced partitions improve query latency and retrieval quality. We can have latency issues with large collections, large-scale vector databases, and then we talk about millions of vectors, may have a high query latency. Solutions here are to tune index parameters like nprobe for IVF and EFSearch for HNSW. Consider approximate search to trade minor accuracy for speed. And as a tip, monitor response time and adjust indexing strategy as the dataset grows. We also can have GPU mismatches once we use FAISS, because FAISS supports GPUs. Using a GPU accelerated FAISS with incorrect CUDA versions can cause errors or crashes. As a solution, verify CUDA version matches FAISS GPU build and fall back to CPU if GPU setup is incompatible. As a tip, keep GPU drivers up to date and consistent across servers. And then, as a final slide, metadata drifting out of sync is something else that can occur. Stored metadata like document IDs, source, timestamps, etc. may become inconsistent with embeddings. As an impact, filtering or retrieval by metadata fails, producing incorrect or missing results. We do have some solutions. Always update metadata together with the embeddings and use transactional updates if possible. And this marks the end of this chapter. And it was a long chapter. It contained even more slides than I anticipated. So I guess that the final chapter or video of the chapter will be approximately 1 hour, but you will spend more time once you start creating and testing with the scripts. But this is all very necessary information, especially when we talk about RAGs. We just did the first 2 steps of RAG. So we talked about the embedding and the indexing, and in the next part of the pipeline, in the next chapter, we will talk about retrieval and generation. So retrieval to find matching numbers for a query, and generating to use matches to create answers. That is something we are going to discuss in the next chapter, but first try to focus on this specific part. Know that we have some different embedding and indexing strategies and when and how you can use them. So I hope that this chapter was interesting to you, that you've learned a thing or two. And if you did, please consider liking this video and subscribing to my channel, because this will help this video, all the other AI Red Team Academy videos, and of course all the videos on my channel. So thank you so much for considering on subscribing. And I guess it is a good thing to do, because if you like this video, you will probably like a lot more videos of me. And I know that most of them are in Dutch, but I guess you can still follow them along by using the subtitles. Finally, another thing to consider is by becoming a Patreon, because Patreons will get a lot of extras and things that are not published on YouTube. So yes, there is already a lot on YouTube, but there are still extra lessons that give more context and more deep dives, and you will get access to these specific lessons in the Patreon section. So they will not be on YouTube. And then again, patrons get some extra videos, have the ability to join workshops, AI work sessions, and you will get the slides, you will get the scripts. So yes, there's absolutely a lot in it for you by becoming a patron, but I guess that the best thing is that you do support the work and you do support this course. So thank you so much for considering becoming one. And this really marks the end of the 12th chapter. So thank you so much for watching and staying with me. And I'll hope to see you again in the next chapter. For now, have an amazing day. Love to see you next time. Bye bye.